Okay, I thought I'd work through another example of transforming a system of equations into reduced row echelon form. And so I thought I'd take a look at exercise 1.1.15 out of the text, where we're asked to fit a quadratic expression through 3 points. So the problem is basically to find values for A, B, and C. Those are 3 unknowns, so that a graph of y equal a plus bx plus cx squared goes through these 3 points. So let me flip over to the whiteboard. So this is exercise 1.1.15, and we're given this expression: y is equal to a plus bx plus cx squared. We want to find values of a, b, and c so that this curve goes through these 3 points. Okay, so what I'll do is plug these values of x and y into the given quadratic expression, and I'll come up with 3 equations and 3 unknowns so for a, b, and c. So plugging in the first point, x is equal to -1, y is equal to 6. So I have 6 is equal to a, and x is equal to -1, so -1 times b, and x squared with x equal to -1, x squared is 1. So this is my first equation. For the second point, x is equal to 2, y is equal to 0. So I'll have a plus 2b, and then 2 squared is 4, so 4c. And finally, for the third point, y is 2, x is 3, I have a plus 3b plus 3 squared is 9, 9c. So, so this is the linear system of equations that I want to solve for a, b, and c. The corresponding augmented matrix is 1, -1, 1 for the first row, and the constant term there is 6. And then for the second equation, I have 1, 2, and 4. It's my coefficients. My constant term is 0. And then 1, 3, and 9 with a constant term of 2. So trying to get this into reduced row echelon form, what I want to do is make sure I've got a leading one in this first column. So I'm gonna leave the one here that's in the first row, and then try to eliminate the first term and the rows below that. And I can see in this case I can do that quite simply by taking, and I'm going to keep the first row, so I'll just copy it down: 1, -1, 1, and 6. And then I'll take the old row 2 and subtract row 1. Again, that's one of my elementary operations for matrices. I can subtract any multiple of a row from another. So if I do that, here I'll have 0. 2 minus a -1 is going to give me 3. 4 minus 1 is 3. 0 minus 6 is -6. And then also to eliminate the leading term in row 3, again, I can just subtract row 1. I could just as easily subtract row 2 to get a 0 here, and then I'll get a 4. 9 minus 1 is 8, and then 2 minus 6 is a -4. So I'll write all the operations I'm doing for each row here next to the matrix, and these actually refer to the rows in the previous matrix. Okay, so now I've got a leading one in this position. I want to get a leading one here. Certainly I could divide this by 3. Usually what I do, instead of doing any division at this point, is I'll try to eliminate all the elements in the same column. This is going to be corresponding to my leading variable, so I'll try to eliminate all the other elements in that same column and retain that leading element. So what I can do here is, I see if I multiply row 1 by 3 and add it to row 2, what I'll do is get a 3 here, but I'll get a 0 here above that leading term, which is what I want. I'm not worried about keeping this a 1 at this point, okay? But so 3 times the minus 1 plus 3 will give me a 0 there. 3 times 1 plus 3 would give me a 6 here. And then finally 3 times 6 plus a negative 6, that's going to give me a plus 12 here. And then I'm going to keep row 2. Okay. And then now I'm going to do the same thing to get rid of this term, the 4 that's below the leading element here. And I can see I can do that if I multiply the third row by 3 and subtract 4 times the fourth row. Again, this is really not one of our elementary operations. It's actually a combination of 2. I'm actually multiplying the third row by 3, which is one of the elementary operations, and then subtracting a multiple of another row, but I'm kind of combining those. And I did the same thing up here as well. And so I see when I do this, and I'll maintain this leading 0 here. This next term will be 0. And then here I've got 3 times 8 minus 4 times 3. So it's going to be 24 minus 12, or 12. And then finally, for this last term, I'll have 3 times minus 4, which is minus 12, plus minus 4 times minus 6 is 24. So that will give me 12. Okay. Now I'm going to simplify this a little bit. I see, in this first row, all of the terms are multiples of 3, and that's true for the second row as well. This third row is all the terms are a multiple of 12. So if I just divide by 3, simplifies it a little bit. So this is just row 1 divided by 3, 0, 1, 1 minus 2. This is row 2 divided by 3. And then row 4, I'm going to divide by 12, 0, 0, 1, 1. And this is actually the row echelon form. Again, I could use back substitution to solve for A, B, and C. I see, for example, right now that C is going to be equal to 1. I could take that value of, and in the previous row I've got B plus C is equal to minus 2, so I could take that value of C equal 1 into this equation and solve for B, and then take that value of C actually and often B back up into the first row and solve for A. But I'm going to do a little more work and get this in reduced row echelon form. And reduced row echelon form, I need zeros above and below all the leading ones. So I've got zeros below this leading one. I've got zeros above and below this leading one. I need to get zeros above the leading one and the third row. But again, that's going to be relatively easy to do. I see that if I just subtract from the first row 4 times the third row, I'm sorry, 2 times the third row. I want to get rid of the 2 here. So I'll have 1, 0. Again, these are zeros here. 2 minus 2 is 0. And then I'm going to have 4 minus 2 times 1, or 2 here. And then in this second row, I want to get rid of the 1 here. I can actually just do that with this elementary operation, just subtracting row 3. So I have 0, 1, 0, minus 2, minus 1 is a minus 3, and 0, 0, 1, 1. And then now this is in reduced row echelon form. Okay, and I get immediately that the solution is a is equal to 2 from the first row, because the corresponding equation would be 1 times a plus 0 times b plus 0 times c is equal to 2. So that gives me a is equal to 2. Similarly, from the second row, I get b is equal to minus 3, and then c is equal to 1 would be the solution to this linear system of equations. And I can take this solution, plug into any one of these equations, and verify it. So if we plug into the first equation, a is equal to 2 minus a negative 3, that's 5, plus 1 is 6. We're into the second equation, 2 plus 2 times a negative 3 is negative 6, so that would be minus 4 plus 4 is 0. And then finally here I'll have 2 minus 6, which is negative 4. Is that right? 2, I'm sorry, minus 3 times 3 is negative 9. So 2 minus 9 plus 9 is 2. So the solution verifies, plugging the solution back into the linear system of equations verifies the solution. Let me quickly flip over actually here to MATLAB and show you how that we can solve this problem. Setting aside the graphics tablet there, solve this linear system of equations using MATLAB. I'm going to enter in my coefficient matrix for this problem. That was 1, minus 1, 1, and I can separate the rows by a semicolon. 1, 2, 4, another semicolon, 1, 3, 9. So this is my coefficient matrix. My constant matrix is 6. I'm just going to enter it in as a row vector and then use the apostrophe to get the transform of it. I'm sorry, the transpose of it. So that'll convert it into a column vector. My augmented matrix is, B just adjoined with A. So this is now my augmented matrix that corresponds to the original linear system of equations. And conveniently, MATLAB Octave has a function called reduced row echelon form, or RREF, where I can just pass it M, and it will reduce the system of the matrix to reduced row echelon form. And this is exactly what we got with our hand calculation. I get immediately A is 2, B is equal to minus 3, and C is equal to 1. So Octave MATLAB makes it very easy to check your hand calculations when you reduce the problems all the way to reduced row echelon form. The reduced row echelon form of a matrix is unique. So whatever we get with Octave should match our hand calculations.